Okay, so thanks everyone for joining today. The idea of this webinar is really to get beyond the buzzwords, as our title suggested. And this, I thank Derrick Turk actually for bringing up this idea. We're going to explore what skills we might need as data-driven petrotechnicals to adapt to today's changing oil and gas environment. For those of you who don't know me, my name is Dylan Lougheed. I'm a co-founder of Saga Wisdom, Inc. Many of you might know we're building online learning tools for subsurface petrotechnicals. I'm going to introduce you to my co-host, Bimal Mehta. Bimal is Senior Vice President, Energy Intelligence at JWN Energy, where he leads the group's efforts of business intelligence and strategic insight. Bimal is going to reflect a little bit on his experience building or integrating machine learning tools into some of their technology. And he's also going to give you a little bit of a briefing on his experience with dealing with some of the vendors that are, of course, heavily selling and marketing to our industry. So without further ado, I'll turn it over to you, Bimal.
Great, thanks, Dylan. So hi, everyone. I'm just going to pop up my screen here. So many of you know our organization. We're JWN Energy, but you often would know us under one of our brands, either the Daily Oil Bulletin, Can Oils, or JWNenergy.com or Evaluate Energy. And we're a broad provider of news, information, intelligence, data to the Canadian and global oil and gas industry. And through the course of our work, we've come across a tremendous amount of focus on AI and machine learning. One of the early views of this was through our intelligence platforms, EE and Can Oils, where there is growing investor interest and pressure in these areas. So often the pressure comes right at the top, at the C-suite, the EVP layers within your organization, as businesses that are looking at valuations are certainly looking at companies like Amazon and Google and Apple, who are all massive users of machine learning and AI, and wondering where's the opportunities in oil and gas. And you'd see a really big shift as we look at the reporting coverage we do of 700 plus companies, of how much time they spend talking about their data intelligence machine learning journey. And often many of you on the call would find that pressure coming top down from your org chart. With that push also comes the need for marketing. And we've, because of our media arm, we get the opportunity to work with a lot of different technology players. Two that are big in the AI space are Amazon Web Services, or AWS, and IBM. And many of them call on your organization, laying out kind of the future and where the businesses can go. And there's a lot of hype in there. And what we've been able to do is help them sort of tell their story through a series of reports, news, events. And I'd strongly recommend that you go online to jwnenergy.com/reports and download some of these. You'll find some pretty interesting insights in there, and just a lot of it around what are some of the cultural dynamics that are needed to be able to bring these technologies in. And we're also using machine learning in our own businesses, and we're using it a lot with respect to document reading, document tagging, be able to find that nugget of information in a massive data. And it has proven to show that there's some promising results. And, I think what gets me most excited about today's conversation is it's the right conversation at the right time. These technologies are reaching a level of maturity, and they're starting to gain significant traction in our industry. They can provide really innovative approaches, and you're going to hear a lot about that today. And the cost to deliver has never been lower. This isn't the realm of the super majors or the largest corporations in the world. These tools have never been more inexpensive to access. But I think what's incredibly important for professionals, and I think it's going to be a big part of today's conversation, is there's a great deal of confusion about when and where to use these tools and how to use these tools. And having spent a lot of time with these organizations and stubbed our toe a few times, our view is it can augment, it'll be a critical part of our future, but it will not replace physics-based engineering approaches. It's really about using the right tool for the job. So with that opening, I'd like to introduce our moderator today. Our moderator is Brian Emerson. He's the data science lead at Petronas Canada. He's got broad experience in the industry, having worked as a geophysicist, also with Talisman and Repsol. And we're pleased to pass it over to you, Brian. So welcome.
Thanks, Bimal. Appreciate the introduction. Can I just say it's a pleasure to be here today. I'm really looking forward to the presentations and discussions. I'm fortunate enough to have seen a few of the slides that are going to be presented, and it looks like a very entertaining set of presenters and certainly a very knowledgeable set of presenters. A little bit of bookkeeping. Q&A can be submitted via the Q&A section in Zoom for those of you joining the live conversation. And we'll also be displaying a poll per presenter, not at the beginning of each presenter's presentation. So just watch out for that. Take a couple of seconds to vote in the poll at the beginning of the presentation. So without any further introduction, our first presenter is Shahab Mohaghegh. He's professor of petroleum and natural gas engineering at West Virginia University, and he's also the CEO of Intelligent Solutions Incorporated. He has a long career working in R&D and the application of machine learning to oil and gas development. He's going to be talking today about the future of petrotechnical work in the 21st century. Shahab, over to you.
Thank you very much. Let me share my screen. So this is the future of petrotechnical work in the 21st century. Specifically has to do with how AI and machine learning is going to impact the future of engineering in general, and then specifically in our industry, in petroleum and natural gas industry. I'm going to start by talking a bit about just a couple of slides on scientific evolution, which in cases it actually was a revolution. Then I will talk about the 21st century engineers and scientists and what is it that they must be exposed to and have knowledge of, which has to do with AI and machine learning. I'll provide a very short definition of these technologies, and then talk about the engineering application of AI and machine learning and how is it different with other applications or non-engineering application of this technology. And then we'll go, finally, I will talk about petroleum data analytics, which is the future of petroleum engineering. So Homo sapiens about 70,000 years ago moved from East Africa to Europe, Asia, and East Asia. In the Europe and Asia, they dealt with Neanderthals, and in East Asia, they dealt with Homo erectus. And the difference that they had this cognitive way of dealing with things. And it took them a few tens of thousands of years before all the other hominids were no longer existing, and it was all about Homo sapiens. And it took tens of thousands of years until about 12,000 years ago, we had the first revolution from a scientific point of view, the agricultural revolution. And that changed a lot of things. No longer, the Homo sapiens no longer interacted with each other in the way they did prior to this and then it took literally another several thousands of years until mid-century that industrial revolution happened. And it changed the dark ages in the Europe and started the age of enlightenment in there. And what was happening to Europe prior to this industrial revolution, and it was all about China and the rest of the world that were much higher than Europe. Europe literally changed everything. Of course, it took more than 250 years ago before this industrial revolution could completely change our society. And now, since mid-80s, we have the things that are happening in biotechnology. I'm sure you probably have heard of CRISPR-Cas9 and what's happening in biotechnology. And then AI and machine learning, they came Of course, AI started in early 50s, but the version of it that we are dealing with right now literally happened in the late 1980s and beginning of the 1990s. So what's going to happen in the future as we go to the, now one of the things I need to mention, what it took a long time for agricultural revolution to change things, literally thousands of years. It took centuries for industrial revolution to change things, but it's going to take only decades for AI and machine learning and biotechnology to change our society. So what would be engineers doing in the 21st century, starting probably very soon from now, in a couple of decades? If you go and start studying engineering at a university, by the time you graduate, what you have learned during the 4 years of engineering may no longer be useful simply because things have changed during that 4 years that you were studying engineering at the university. You have learned, the key is you have to learn the fundamentals good enough so you can build on them as you move forward as an engineer in 21st century. You have to learn the fundamentals of the mathematics, the fundamentals of science, and starting today, it is the fundamentals, AI and machine learning, that doing this is going to literally change everything in how we interact from an engineering point of view in all different engineering disciplines. One of the things, the key is you have to learn how to learn during your engineering process rather than becoming a complete domain expert. You have to become a complete domain expert, but you have to know that things are going to change quite quickly. So as an engineer in 21st century, above and beyond your domain expertise, you must keep an open mind and learn. And keeping an open mind is incredibly important because things are going to change more and more. And you have to understand the contribution of AI and machine learning to what is going to happen. This is required for the 21st century. And now, since we keep talking about AI and machine learning, let's identify a few definition of what these are. Artificial intelligence is defined as the technology that mimics human brain for analysis, modeling, and decision making. The next item is machine learning. Machine learning that contributes immensely to artificial intelligence uses open computer algorithms to learn data, to learn from data instead of explicit programming. What we do until today, when we build computer programs, we tell the computer through program to do everything to incredible detail. Now, the difference in the machine learning is you don't do that. You provide an open computer algorithm that it can learn from the data that you provide. And of course, then it's deep learning, which is pattern recognition using neural network and multiple layers of hidden neurons. So what would be the future of AI? While the new version is purely based on data, and incorporation of a rule-based system was completely avoided in mid-1980s because that's what it was used to be called AI. And that's why in 1990s, nobody called what we call today AI, nobody called them artificial intelligence simply because artificial intelligence at that time was a purely Aristotelian logic-based, rule-based system. Now, in my opinion, what's going to happen is non-Aristotelian logic, the way human brain works. Aristotelian logic is a two-value logical, yes, no, black, white, 0 and 1. Our brain does not work in that fashion. And building intelligent system and using non-Aristotelian logic, it can be combined. That would be with the data. And to me, that is the future as we move forward with AI. So let's talk about the engineering application of AI and machine learning. There are differences between engineering problems and non-engineering problems. When you solve non-engineering problem, you require general intelligence. You do not require domain expertise. However, when you're trying to solve engineering problems, you require domain expertise. For example, in convolutional neural network that was generated in 2005, 2006, by Google, one of the major items is image recognition, recognizing between, let's say, cat and dog, if you use the ImageNet data out there. So the question is, in order to be able to recognize between cat and dog, do you need, what kind of domain expertise do you need? You really don't need one. A 5-year-old can do that. Please do not get me wrong. This does not mean that's an easy thing to do from an AI point of view. It's extremely complex. However, it does not require any domain expertise to be able to do that. For example, right now AI used in face recognition. It is used in object recognition, identifying which one is a car, which one is a bicycle, which one is a pedestrian, whether it is you or somebody else that's opening your iPhone. These do not require domain expertise. Voice recognition. Anybody, a 2-year-old child can understand the voice, whether it's his dad or mom or somebody else. Even the anyways, issues such as translations, other things such as caption generation, which is used LSTM, literally what it does, it identifies a picture and then it identifies how you can caption this picture through AI and machine learning. Now, none of these that I talked about until now, none of these has anything to do with engineering. Or in other words, you don't need domain expertise to be able to do any of that. To drive, you don't need a bachelor's degree or a master's degree. Without even knowing anything, you still can learn how to drive. So that's not an engineering approach. So, but what if somebody tells you, okay, you have yellow dots and you have black dots. Can you draw a line to separate these two? And if you ask that from a 5-year-old, don't you think he or she can do that? And the only thing is, it's a nonlinear separation. He or she can draw that to separate this. But what if you ask them, no, I want you to separate those, but I want you to do it through a linear separation. You should not be a nonlinear, it should be a straight line. Can you separate these with a straight line? Now that, a 5-year-old probably no longer can do that. Why? Because it needs to understand the mathematics behind it in order to be able to change some things, then be able to separate it with a straight line. It's still possible, but it requires domain expertise to a certain degree. So the complex examples that we deal with, for example, what is the engineering approach of trajectory when you throw something and somebody catches it? Does human brain does the same thing? It develops an equation and then tries to solve it in order to catch the ball. What about doing this? It's called inverted pendulum, where a 5-year-old can do that. But using it from an engineering point of view to model that, it's going to be incredibly complex. And unless you use AI, literally, you cannot do that. But you have to use it in the application of the AI, engineering application. So the key is, does human brain builds equations and then solves them to find solutions? Well, the answer is no. That's not how human brain works. Human brain observes, uses experience, and does a lot of trial and error, and uses the dendrite and the axon and create the synaptic connection in order to learn. And the key is, how do you solve engineering problems using the way human looks at it? This is a completely different approach than using equations and our physics-based traditional mathematical way of doing that. And that's what separates these two different way of solving problem. So the importance, but it all comes down again to the domain expertise. the using AI and machine learning to solve a specific engineering-related problem. What is important is to have domain expertise in the specific engineering discipline that you're trying to apply this to, but that's not enough. You must be a good and a strong AI and machine learning practitioners and have expertise in practicing it, not necessarily its fundamentals. And this is my view of how engineering application of AI and machine learning has to be. At least 50% of it has to be domain expertise, and the rest of it has to do with AI and machine learning and forward. So one of the major issues that exist, people think if they just learn, what's to a certain degree, I find it to be unfortunate that right now we have 500 billion, we have 7 billion human beings, but we have 500 billion data scientists these days, if you go through LinkedIn and look at it. Because people think if they understand very simple thing, then they become data scientists and AI and machine learning experts. What my understanding is that's not really true. In order for you to become an expert, a practitioner, and knowledge of AI and machine learning, you end up becoming very interested in philosophy. You become very interested in neuroscience. You become very interested in computer science and statistics and biology and mathematics. But these three are the main things. And if these three items do not interest you, then there is something wrong with how you approach AI and machine learning based on my understanding. So now, when this is applied to petroleum, we call it petroleum data analytics. And one of the issues with the petroleum data analytics these days are that they have two parts of it: data analytics and big data analytics. And a lot of people think they are the same. They are not. Data analytics uses current existing data to build models for optimization and decision making. Big data analytics is a different approach to AI. Using real data, real-time data to build model optimization. We can do that in the petroleum engineering. However, they're not the same thing. That's another thing that people do, in my opinion, misunderstand. For example, if it's only data analytics, we can apply it to reservoir engineering, to completion engineering, things such as historical production, injection, core analysis, well test, completion design, hydraulic fracturing. These use data analytics. For big data analytics, you can apply it to MWD and LWD and DAS and DTS, fiber optics, ESP, seismics, and so forth, because you have incredible amount of data. And what goes in the middle is literally formation evaluation, which is mainly well logs. And of course, when you go with gas lift of artificial lift, it could go in both ways, depending on what kind of data that you have. Finally, what I would mention, this is last two slides, is that engineering application of AI has two parts. One is purely data-driven, and that it requires making sure that physics is honored. What today people are calling explainable AI. We've been working on that for about 15 years and have a lot of way of explaining. It's, for me, AI and machine learning is no longer a black box. We can explain it completely what it does. It requires engineering expertise, AI expertise, honoring the physics, understanding the physics, the knowledge of it, not the equation of it, validation of the physics, and using intelligent agent. However, you can go ahead and use physics-based data-driven. We call that smart proxy. And that is when you use equation, whereas through analytical solution or numerical solution to generate the data, and then you use smart proxy using the data that came from equation. But what's different and unfortunate, in my opinion, when people combine these two, they call it hybrid model. Combining real data and equation, it lacks the expertise in engineering if you are an AI expert, but it lacks expertise in AI if you're an engineer. In other words, what the whole reason behind AI and machine learning and purely data-driven is avoid assumption. And if you do data-driven through equation, that's perfectly fine. But if you combine these two, you're literally undoing what AI can do for you. But if some people do not do that because of that, they use it mainly as a marketing scheme rather than anything else. This is my last slide based on the key word that was used for this webinar, which is called buzzword. So my question to you is, if a company come and tell you that I can make you a master reservoir engineer in just 1 month, What would be your take of that? This is not real, by the way. No company has ever done this. I'm making this up to make a point. What if a company tells you I can make you a master physicist in 1 month or a master statistician in 1 month? Does it make sense to you? I think it's clearly obvious. Now, this one is true. This is a real marketing advertisement that people have done, that they says they can make you master data science in just 1 month. And that ends my presentation, and hopefully it was 19 minutes. Thank you very much.
Thanks very much, Shahab. That was really interesting. I have a couple of questions for you, Shahab, based on what you've just been through. It's pretty typical at, say, conferences and so on for someone to stand up and give a data-driven analysis of, let's say, well performance or similar. And there's usually the fairly cynical question from the back of the room that says, have you tried or have you looked at any physics-based methods? And often the presenter hasn't, because they're, as you alluded to, a kind of they're a data professional, they're a data scientist or similar, and they've taken that approach. If you're not a fan of bringing those two things together as a kind of combined analysis, how do you think you should reconcile the two when presenting them to an audience of management or decision makers or even to technical professionals?
I think it's very important when you deal with these management people that for you to be a domain expert. And that's one of the things a lot of people dislike about some of my presentations when I go and talk to specific companies. They say, you keep talking about reservoir engineering and hydraulic fracturing, you never talk about data-driven issues. And I say to them, but the key is you have to be a domain expert to be able to use AI in a fashion that makes sense to these people. If you don't do that, if you only have a purely statistic-based approach, then they're truly correct. They tell you you don't know what the physics-based is. Now, the only thing that's different here, the keyword physics-based, in my opinion, when it comes to AI and machine learning, has to do with knowledge, not equation. Specifically in our industry, because none of us have been 10,000 feet under the ground and actually saw what's happening. It is based on incredible amount of assumptions that we make. And I'm not saying those assumptions is incorrect, but it's different. Therefore, the AI approach to building physics-based model is through, if you call it hybrid model, it's the combination of your knowledge, not combination of equation with the data.
I see, very interesting. I have a question from the audience. Are there any other areas in operations other than production automation where machine learning can be readily applicable, taking into account the issues that we have with unstructured data? So where do you see other applications of machine learning to providing value in the oil and gas sector?
I truly believe that everything that you do in oil and gas industry, as I gave you those lists, they definitely data-driven AI approach can contribute to it. We work a lot in reservoir engineering, in hydraulic fracturing and completion design, and in others we have done in drilling, and right now we're doing a lot of work in production optimization. The key is today we have access to fiber optics, and that, in my opinion, that fiber optics can change everything when it comes to shale in our industry, simply because it provides a lot of real data. But if you don't use AI to learn it and you try to use equation, then it would take you a lot of time and effort, and I don't know if you'll be successful.
We're about at time for Shahab. So Shahab, thank you very much for your presentation. Really enjoyed it. Our next speaker is Derrick Turk. He's an independent data science and technical computing consultant, and he supports the E&P industry from his firm, which is called Terminus Data Science. He has a broad background in reservoir engineering, and today he's going to be examining how data-driven technologies relate to petroleum and petrotechnical engineering, and specifically to petrotechnical and petroleum engineers. Derrick, over to you.
Thanks, Brian, and I'd like to thank everyone at Saga for putting this event together, as well as thank all of you for tuning in this morning. Well, my talk is called Disenchantment, or There Is No Magic, Only Engineering. And what I want to do today is deconstruct what I call nouveau tech for petrotechnical professionals, which I think are the bulk of our audience. And by nouveau tech, what I really mean is sort of the buzzword soup of data science, AI, ML. You know, it wasn't too long ago, and I think it's coming back, that there was a surge of, you know, learn to code, or what have we heard lately? Low code, no code. So let's dig in a little bit. Let's try to see through the buzzwords. Some quotes to set the mood. Euclid said, "There is no royal road to geometry." In other words, there are no shortcuts where we're going. Richard Feynman, the physicist, gave an interview in the late 80s where he talks about the misconception, very prevalent misconception in the world, that math, and I would say quantitative disciplines in general, are sort of uniquely inaccessible, that you have to be born with a math gene. And he says that's not true. Math is a human discovery, and it's no more complicated than humans can understand. What one fool can do, another fool can. And finally, a kind of funny quote I like from a play where a character finally learns from someone he's talking to the definition of prose versus poetry. And he says, "These 40 years now, I've been speaking in prose without knowing it. I want to make the case today that many of you have been speaking in software without knowing it." My thesis is this: if you want to learn data science, machine learning, AI, or any other modern tech buzzword, the path to true understanding starts with programming. If you're in a petrotechnical profession, you are probably already a programmer in a very real way. And in any case, you are well equipped to learn the skills that you need. You learn them just like any other engineering skill, from the fundamentals. So when I first began talking with some of the folks at Saga, as well as some of the other panelists, about the concept that would become this webinar, I came up with a thought experiment. My thought experiment was this: if I had a time machine and I wanted to go back to ancient Greece and explain machine learning to, you know, an educated, intelligent ancient Greek, but still a person of their time, say Socrates, right, as kind of a funny example, what concepts would I need? In other words, what common language would we need to make this plausible? And after thinking about it for a while, I came to the conclusion that I don't really need calculus. I think I can kind of give them a high-level overview of the pieces they need. Statistics, linear algebra, I think we can cover that. What would really help me out, though, is if Socrates knew a little bit of basic Python. So I'm not going to play this entire clip. You can view this in the slides, which I'll make available later, or actually watch it on my blog. But I kind of wrote a dialogue in Python between Socrates and Plato, and they kind of talk through, you know, at a super high level, what is machine learning, and you know, what is a plot, right? So he kind of shows how to compose a plot and fit a model to data and so on. My point is that in order to really make sense of machine learning, we've got to have the common language, right? We've got to be able to understand software and software development, because there is no magic. There's only engineering. Programming is an engineering discipline, or at least it can be one under the best conditions. Just like any other engineering discipline, we solve concrete problems under constraints. We do it by applying quantitative techniques and knowledge of first principles. It's also a creative discipline. It can be a little bit of a craft or even an art. Just like any other engineering discipline, I was a mechanical engineer by training, so I think of things in terms of mechanical engineering, very concrete. We can think about building up our knowledge of programming and computer science from the bottom up. Kind of a bad habit, I keep a log of my favorite insults I've ever received, often because they don't quite land the way the person who launched them meant. And I think my second favorite of all time was in a fairly heated internet discussion about machine learning. Somebody accused me of being a reductionist, and I said, well, heck yeah, I'm a reductionist. Because a reductionist is just someone who believes that to understand a complex system, you break it down into its smallest component parts, and you sort of build up your understanding one layer at a time. Well, we can do that in engineering, and we can do that in programming. These are not unattainable things for most of us, you know, in the audience today, who are likely engineers, geologists, or technical professionals. What does get in the way perversely, is the explosion of content on the internet, and perhaps better said, the explosion of content marketing. So in the spirit of Mark Twain, who dug up in the late 1800s and sort of popularized, made infamous maybe, this Portuguese to English phrase book called English as She Is Spoke, I'd like to talk about some of the idiotisms and proverbs of computing as she is spoke in today's world, because I think this trips us up. So this is kind of my, with apologies to Ambrose Bierce, this is kind of my devil's dictionary of computing marketese to English. I'm not going to belabor these. A lot of these are kind of intentionally glib or maybe dysphomistic. But my point is we've got to learn to see through the hype. When people talk about things like big data, more often than not, what they mean is, well, I naively tried to load this file into a single pandas data frame, and it didn't fit in memory. It's big data. Better use a distributed, Spark or something. And that's crazy, right? That comes from sort of a superficial understanding. When I see a product marketed as artificial intelligence these days, about the only thing I know with any degree of confidence is that somehow, it involves a computer program. I think the joke I saw recently is that if it's written in Python, it's machine learning, and if it's written in PowerPoint, it's AI. Machine learning, right? At the end of the day, what machine learning really is, and this is not to belittle it, but it's to make clear the limitations. It is curve fitting with a computer. It is minimizing the error of some model against observed data through a computer algorithm. Nothing more, nothing less. And so the ability to write, and in fact, almost more importantly, the ability to read software is extremely critical to understanding the application of machine learning and understanding how to build and deploy your own machine learning projects as an engineer. I'm fond of some of these others too, NoSQL and blockchain. I think that's been a little bit interesting to watch over the last few years, the slow decline and rebirth of the relational database, but that's a topic for another time. The other piece of the case I want to make is this: you're a wizard, Harry. One of the issues that comes up over and over again in computer science education is a sort of elitism backed by a certain amount of superficially plausible research. So this was a famous paper from 2006 called The Camel Has Two Humps. These researchers claimed that they had found a reliable pretest that could determine which of two populations an incoming computer science undergraduate fell into, either they called them the programming sheep or the non-programming goats. And the test had a lot of questions like this. The premise was you answered these questions, what does this program do effectively, except you haven't taken the course yet. And they said, well, if your answers show a consistent mental model, you are one of the chosen few. And if they don't, you are, cast out into the outer darkness. You'll never learn this. So I look at this, and it actually reminds me of the research that shows things like the SAT are biased, because the SAT on the verbal portion will ask questions that are like, okay, analogies. A yacht is to a catamaran as a sloop is to question mark. And, I don't know, I didn't grow up around boats. Like, what the heck is that? Well, in the same way, if you didn't grow up, or in other words, if you don't have sort of background familiarity with an algol-like, or I guess in modern terms, a C-like language and syntax, where the equal sign is a mutable assignment operator, this doesn't make much sense to you. It's kind of silly. And in fact, they retracted the paper about 7 years later. This didn't get as much publicity, but they said, look, our claims were actually, the data was not strong enough to support these claims. They backed off. It's actually a pretty interesting retraction if you read it. But we still do this. This is an example that I think was pretty typical in the engineering programming courses I took, and likely that many of you took, where they ask you to interpret some mystery program. Variable names are kind of obfuscated. And what does it do? It's this very operational reasoning type question. This is silly. This is like asking sixth graders to interpret Finnegan's Wake, and from that somehow inferring their skills in English or in reading. It's just so alien from the way the language is deployed in day-to-day use. What does this program do? Think about it for maybe 10 to 15 seconds, and I'm quite serious when I call it a program. Right, so hopefully it's a familiar programming language. So hopefully many of you caught on by now. It computes the Fibonacci sequence, right? And what we've really done here Wow, that's functional programming. In fact, that is functional reactive data flow programming, which is kind of an esoteric paradigm in academia, except that it's also the most popular programming language in the world. And if you really dig in and think about the way you can drag cells down a spreadsheet, functional programmers would say we're actually working with co-recursive streams. So my point is actually, in a Harry Potter analogy, it's deeper than you're a wizard, Harry. My point is there are no wizards and there are no muggles. Anyone can do this. Almost all of us are already programmers in a very real sense. We have the skills. In a longer talk, this is where I would dig into some really crunchy, concrete case studies and lay out some detailed hints for how to proceed with kind of baby steps. We don't have time for that. So I've got resources in the tail end of my slides. I suggest you check them out. There's a pretty long bibliography. I think many of us on this panel are actually working on better ways to train some of this stuff. But what I would like to talk about is something that's not typically covered early on, and that is some hints on how to design software systems in ways that make them useful in the long term. The first hint I would give, and there's a great talk that probably says this better than I can by Rich Hickey, designer of Clojure programming language, called Simple Made Easy. But I want to claim that simplicity is better than complexity, and that simplicity is longevity. My example, without belaboring it, would be to compare the American space shuttle with the Russian, or formerly Soviet, Soyuz capsule. The space shuttle is a triumph of engineering, but is also an extraordinarily expensive white elephant and sort of an exercise in design by committee. Its useful life was shorter than expected, and it proved to be, much more limited than I think many of us hoped. The reason for that is it sort of tried to do too much at once, right? And it was a very complex design. The Soyuz capsule, the Russians actually adopted a modular design. They could easily reconfigure it for many different missions. It sort of crash lands in Siberia. They don't worry about reusability. And this proved to be a much more sustainable and viable and long-lived design. In fact, if you look at now the second way to the International Space Station, other than Soyuz, is the SpaceX Crew Dragon, which looks a lot more like a Soyuz than it does like the space shuttle. So to tie it into software, Tony Hoare, the inventor of the quicksort algorithm, and I love this quote, he said, there are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies, and the other way is to make it so complicated that there are no obvious deficiencies. And the first method is much more difficult. The second piece I want to talk about, and I'm excited because this ties into David's case study, which you'll see in a little bit. I want to talk about composability. Composability is the property that's sort of the inverse of reductionism. It's the property that you can build up a functioning larger system by assembling smaller parts in different ways. And I always think of Lego sets. We've got a few different generations on the call, I'm sure. But I perceived as a kid in the 90s that Lego sets were undergoing this transition from the thing on the right to the thing on the left. Where on the right, you have a very composable system, lots of small parts. It might be more difficult. You might need a little more time to build it. It might be kind of blocky. But you can make a Viking ship. You can make a moon lander. You can make a car. On the left, you have a piece that's great if you want to make a car exactly that size, right? But it's not composable. You're not going to build a jet or a Viking ship out of that piece. So composability is a way to let user intuition and creativity combine and reconfigure the pieces you build in novel ways. I'll talk a little bit more about that in a second. Finally, I want to leave you with a dire warning about the life cycle of configurable systems. This is something I see over and over again building software for clients, or even coming in and sort of rebuilding software that clients have already designed, where you start with the new quote unquote elegant system and we don't need all that crap. And then over time, people love it, they use it, they keep wanting to add new features, new options, and then you sort of get something that drowns in its own complexity. And then eventually, you pay someone like me to come in and rewrite back to the simple, elegant system. And anyhow, you get this sort of loop. Now, there are ways to break this. These slides are actually taken from a talk, which is in my bibliography. I'd love for you to look it up, on domain-specific languages, which I think is one great way to break this kind of vicious cycle in software design. So with that, in the interest of time, I'd actually like to move into Q&A. And it's Q&A bingo because I've sort of tastefully obscured some of the most frequently asked questions, and we'll see if we can get bingo. So with that, I'm going to pull up the Q&A and see what's in there, or maybe Brian can suggest a couple.
Thanks very much, Derrick. Much appreciated. You've given me some impetus to talk up my Excel skills, but no motivation to read Finnegan's Wake. So thank you very much for that. I have a question for you, Derrick. What are your thoughts on no-code or low-code solutions? You know, that you said like a lot of engineers are basically programmers or building their own kind of software. There's a lot of tools out there that mean they don't actually have to get into the nitty-gritty of writing, you know, process flow control statements, etc.
Right.
Are they a great entry to this kind of application, or are they a great way to mislead yourself?
So my answer to that is a frequently asked question. And my answer is, well, yes, but actually no. When I think of low code or no code, or sort of more commonly in our industry, the BI tools that are drifting in the direction of becoming application platforms, Spotfire, Tableau, I think of them kind of like the big blocky car chassis Lego piece. They can be a really efficient way to build something that fits within the confines of a sort of interactive, I guess the technical term is like brushing UI, where the thing where you can sort of mark observations in one panel and then, you know, sort of cross-select across visualizations. They're great for stitching that together quickly. Where I find they fall down is when people try to build more sophisticated machine learning or analytics models inside those. That's getting better in that most of the tools now expose interfaces to languages like R and Python. But where they still really fall down for me is when you start trying to use them as sort of full-on applications, and specifically when you start trying to use them to do data management. I've seen clients, and I've been in these quagmires myself, where you start trying to use something like a Spotfire dashboard as a UI to a database. And it works really well for viewing and sort of doing online analytics on filtered subsets of that data. What becomes very difficult, though, is the management of state in the other direction. It's the pushing back of user-created data to the database, or for that matter, it's even taking user input. So you come up with all sorts of elaborate workarounds, but they all end up involving as much or more code as you would write in sort of a more traditional software application. So there's a blog post on this in my bibliography if you would like to see more of my thoughts, but that would be my short answer.
Great, thank you very much. I have a question from Melanie Pop. Hi, Melanie. Can you make a comment on understanding purpose in system design? She thinks a lot of the reasons we get those big Swiss Army knives is because we don't stay true to what the original purpose of the solution was. So there's this kind of successive scope creep, I guess.
Yeah.
Can you comment on that?
Yes. No, I 100% agree with that. And I think it comes down to, actually like the question said, it's sort of a lack of conceptual clarity. In fact, so to take kind of a broader and popular philosophical stand, I think in some ways the push toward what's called agile development methodologies has been a little bit disastrous, specifically in the world of engineering software. And the reason for that is that it's a philosophy which is very much against what they call big design up front, right? Now, if you think about it, yeah, it's a reaction to sort of some of the IBM excesses of the 90s. But that said, big design up front is another word for engineering. Engineers are trained in functional decomposition and in disassembling a system into component parts with well-defined inflows and outflows. So to me, that one of the most valuable things you can do before you write a single line of code is to sketch out what is the intent of this system. What is the specification in the sense of, you know, what does it take in? What does it produce? What are the conditions for correctness? And then decompose that into pieces and build it. So, you know, I think that's 100% true. I do think the vicious cycle though also creeps in because you can be a victim of your own success, right? A well-designed, simple, elegant, well-spec'd system inevitably draws an audience that likes it and uses it. And because everyone's use case is subtly different, you sort of end up being strongly compelled to add features, and that's where you have to really aggressively fight complexity, right? My opinion is complexity is the enemy in all of its forms.
Yeah, thanks very much.
Not a common question, by the way. It's a good question.
Yeah, yeah. There's another question from Sean, which I think is a question a lot of people have with engineering backgrounds who would see all these new tools available. I'm an experienced reservoir engineer with no programming background. You know, where should I start? And really kind of reconciling, I know maybe not asking you to comment on this, but, you know, should I learn how to program? Should I learn data science? Should I go and get an MBA? And
yep.
Maybe the latter one you don't want to comment on, but
I want to, but I probably should not.
Right, gotcha.
So I would say my answer is that if you want to really understand data science, yes, it is necessary to have a background in statistics. And yes, it is necessary to learn a decent amount about machine learning. That said, data science is, you know, A, it's a very broad and sort of vague term these days. But B, it is intrinsically about computing. I see a push in the industry to try and piecemeal. In fact, I'm going to answer a different question. Because the related question I always get is, why should I care about coding? I'm a data scientist. And my answer is, be a unicorn. There's a push in the industry, not just our industry, I would say the technology industry in general, to sort of differentiate data science versus data engineering versus yada, 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 where each of these is different gradations of, you know, I just know pandas versus I write Spark pipelines versus, and it's, to me, it's completely crazy. Because at the end of the day, the core skill is software design. And that's not to say you have to be a operating system kernel programmer, or you have to write compilers or whatever. But I think as an engineer with an interest in data science, or really anyone with an interest in data science, it behooves you to build a grasp on the fundamentals of programming and of program design. And it's not, for an engineer, it's not that long a journey. We have most of the skills and in fact, most of the sort of philosophical mindset you need to do it. Now, the problem is we're kind of drowning in what I would call introductory material, some of which is written by beginners for beginners. And then to make things worse, we have really a shortage of what I would call intermediate material, or sort of material on how to go from, yeah, I can write functions in Python, or, you know, pick your favorite language. But how do I design programs? And so that's actually something, without giving too much away, I know that several of us on this panel are working on things along those lines. That's something I expect to see improve in the near future for engineers.
Okay, great, thank you. I think in the interest of time, we need to move on to our next presenter, but thank you very much for your comments and for an interesting presentation. So our third presenter is David Fulford. And David is the VP of Reservoir Engineering at Griffon Oil and Gas, and has a long history in a variety of engineering roles with upstream operators, including time as a founding member of Apache's data engineering and analytics team. And I'm really looking forward to what he has to say about composing a data culture, how we as oil and gas and service companies can become data-centric, and critically, how we sustain that data centricity.
Thank you to Saga Wisdom for inviting me to speak today. I'm excited to talk to you guys about what I think is important to follow up with what Derrick was talking about on system design. So what I'm not going to talk about is data science, analytics, machine learning, or more traditional reservoir engineering workflows and production forecasting, reserves economics, or any RTA, PTA type talk. What I am going to talk to you about is data, workflows, and tools. And the reason for that is, you know, machine learning is sort of the sexy end product of the digital transformation, but it needs to be built out of the building blocks of data, workflows, and tools. So that is the destination, but tools and workflows and data are the journey you have to go to get there. So maybe you're in this state where you have these three things and they interact, right? And you feel like things move around pretty well within your personal workflows or your organizational workflows. But most people and most organizations, I think, really fall here, where people are still at the center and doing manual data management and migration, copying and pasting, loading data, or taking output and putting it somewhere. And so what happens is, as we develop this digital transformation, we're just really adding more things that orbit around the people at the center, and it becomes overwhelming. And so the question is, well, how do we make the digital transformation, right? How do we enable AI and machine learning? And again, I think it's missing the fact that you have to go through the journey. You're just trying to say, how can I jump to the destination? What we'd really like to get to in an ideal state is data at the center, and our tools and workflows orbit around that. And then the people are outside of it, and we're able to automate tasks, and then people can then focus on the interpretation workflows, the higher value problems that we can't provide automation, right? We can't deploy machine learning yet. It needs to be developed, right? And where, technical workers can sit and apply their creativity to solve the high value problems. So I think, three guarantees in life are death, taxes, and data cleanup. Any analytics workflow starts and ends with data. Not only do we have to query the data to start, but we have to store our data when we're finished. So think about this. The cleaned, interpreted, and analyzed data is the most valuable kind of data. It's what you pay all those high salaries for your petrotechnical workers to analyze and interpret and build knowledge out of information. But it's often not treated with the same level of care as your raw measured data. So think about how much processed, interpreted knowledge lies in the crypt of plain text files on network shares, as Excel spreadsheets, as CSVs. What is it doing? Is it being related? Is it being used? Is it kind of one-shot analyses that be forgotten about? How much is kept only within the mind of the person that did that and doesn't get transferred to other workers? If we care about enabling a data-centric culture, I think the most important property of our data system is composability. Composability is a system design principle. A highly composable system gives us components that we can select and assemble in various combinations to satisfy user requirements. So each component, if we take Derrick's great image there of a Lego block, it's self-contained, right? You can deploy it independently, and it's replaceable. And so even though they might have a relationship, any specific piece can be taken out and replaced with any other piece. And so they really become more like commodities. And this makes them stateless. And so we think about programming or transactions as requests, right? You could think of a Lego as being stateless. It's independent of all other Legos, right? It's the assemblage of them into the system that matters. And the big motivation for why a composable system is composable systems are more trustworthy because they're simpler. They can be broken apart. They can be understood. You can treat each component as a contract. If I give you A, you must give me B. And we think about engineering rigor, right? For exact inputs, we get exact outputs. That's what we get, is we get much more rigorous parts that we can build complex systems out of. And the complexity is an emergent phenomenon. It's from the interaction of simple systems that begin to interact. And it doesn't take a lot of interactions to create immensely complex processes. All you really need is 2 or 3 functions that chain together, and you get something that can be quite hard for a human to break down those specific steps. So how do we design composable data systems? Do we imagine it, as an engineer might, as a manufacturing line where the parts are assembled into some final product? Well, that's not really stateless, is it? Each station requires some specific state to have added on a part to that in order for me to add my part. What about a pipeline where we combine these data flows into a single stream? Again, the image gives you some sense of, even though we think of oil in a pipeline flowing, that could be stateless, but data itself, when we're preparing it, performing analytics on it, is not stateless, right? And it implies that some modification is occurring. So I think a better analogy is to treat your data like an ever-expanding encyclopedia. Every process edits an existing chapter or adds a new one. The context of each chapter is maintained in a table of contents. Perhaps you have an index. And the chapters themselves could stand on their own, but they do have a rational ordering. And so over time, as we get more data, those chapters expand and our knowledge increases. So I think Python's emerged as the lingua franca of data science, and not just for the practice on the desktop, but for the deployment into production systems. Because more so than many other languages, I think it enables composability, has a good standard kit, and it's easy enough to use as a base programming language. So these tools, this part of the standard kit for Python, I think are useful for data processing, but the built-in tools are quite poor for data storage. We have the ability to serialize objects either as CSVs or Python has something called a pickle, which we can use to save state of an object, but they can't be related to any other data in that state. And then oftentimes if you write text to file, we don't have types conserved. So think about what is the type of an API number? Is it an integer? Well, we can't perform math on it. Is it a variable length string? Is it a fixed length string? We do get some meaning behind API 12 versus API 14. Does it really even matter? And I'd say it does matter. And if you're not thinking about it, then you're going to get caught by some issues. And I'll just say, what about Excel when you open a CSV with API numbers and then you save it? Excel makes some assumption about the type of the API number. And if you don't catch it before you save it, you wiped out actually, I think, 10 of your 14 digits or so with that API number because Excel assumes they're not necessary. So when you have data and you have types and you have a desire to relate them, those are the three features of a relational database, which is still ideal for dealing with structured data with obvious relationships. And more than that, modern database software also offers spatial functions, which is a huge part of what's important about our industry. It's not just the data itself, but the spatial relationships of that data. And so with those spatial objects and spatial functions, we can easily compute things like distances. We can apply, set concepts, intersections, unions, etc. Some examples to intersect well surveys with grids, either structural grids from geosciences, legal grids, counties, lease units, sections, etc. And then, a big benefit is SQL queries are automatically optimized and can be parallelized. And so you write a very declarative structure in your SQL, and the query engine will take that and translate it into probably an ideally efficient way to execute that statement, that transaction. Performance is generally 10 to 50 times over pandas data frames. And if you're comparing non-trivial, vectorizable operations that don't have built-in, low-level implementations in Python, it can be even faster than that. So what can we do in SQL? Well, some examples, we can construct and use spatial geometry objects, such as we want to list all wells within n miles of a selected point, and we can use this for parameter averaging. We can use it for distance weighted averages. And we can use it primarily, I think the most simple example is to impute missing values. If I have a well that's missing some data point and I know there's a spatial relationship with that, I can use some average to impute that. And I think research shows models that use imputed data perform better than models that simply truncate data rows or columns with missing values. We can start to construct geometry objects from public data. And so if we have public surveys, well deviation surveys, we can build those into line streams. And then we have automatic sticks on a map, which seems to be all the rage to do in PowerPoint. We can then intersect those wells with structured grids and do things like automatically tag formation and bench of those wells, given we have some map structure across a basin. So some examples of this. Think about a case where you had some area of interest. We'll call this a region, and we want to know maybe my sample size isn't large enough for an analysis I'm doing. We can buffer that polygon and then intersect it with our wells and find wells that fall within some radius of that area of interest. This is also useful for finding neighboring regions. So if I had some region-based properties and I wanted to understand, okay, well, what about the areas around that? It's very easy to buffer that and run a spatial intersection to get a list of all the regions nearby, and then build a composable workflow out of that. I don't need to have a preset list. I can change these polygons at will, and my workflow still works just as well as it did if I had a static list and non-changing polygons. We can begin to do things like hierarchy-based regression. And so obviously public data has a lot of issues, just noise. Sometimes you can't determine parameters of a regression process, or sometimes the data is missing. So if we think about, from the most lowest level to the highest level, perform some type of regression, and then coalesce or impute those values on the way back down. And I'll show you this in this next slide to kind of illustrate this a little better. But think about constructing a table of base decline parameters for forecasting wells with minimal production history, right? And in the absence of data, what is my base expectation? Well, that's probably going to be wells that are close to it with similar features. This is especially useful when we think about associated gas and water, GORs, WRs, where the public data is usually quite poor. So the way we would do this is we go from well formation bench up, and we regress, perform a regression at each level, right? And then we go back down and we coalesce, or if null, whatever your database software uses for filling in null values, we go back down. And so we're getting, in the absence of specific data, we're getting some imputed value. And in the end, we're able to create a value and fill in, for every single well. And so we have, we don't have to truncate anything out of our data set. We're able to make use of all the data. We can also do things like write functions in SQL. So what I've done is I've implemented a hyperbolic model into SQL. And so we, every night, regenerate forecasts on every well in the Delaware and Midland basins, which I think is about 35,000 horizontal wells. It takes maybe 5 or 10 minutes to do all that. It's very fast. And then what this gives us is the actuals plus the forecasts are available via query with no lag time for computation. We don't need to re-implement decline curves for each use case in several different languages and then validate that code gives the same answer. Instead, we get a single source of truth for forecasted volumes. We can build an interface on that wherever you'd like to see it. A centralized SQL infrastructure is low cost. There's no need for middleware to handle interaction between local machines and that SQL server. End users can sort of self-serve the data they need. As much as we can, we move data to process on the server where it resides, and we do it at night when no one's needing to query things. We have zero bandwidth costs. So if you are going to a cloud infrastructure and you're worried about that, that's a big key factor, especially for a startup where you're very cost conscious. We also can migrate low compute Python tasks to the cloud. We have actually a single Linux machine where we've set up a reverse proxy to host multiple web servers. That single machine is 4 gigs of RAM, has 1 virtual CPU. It hosts a RESTful API. It hosts Apache Airflow for task management. It hosts Jupyter Lab for like Jupyter notebooks in a shared code space. We can host single page web apps on it, static page apps, and we actually even host our own private Python package repository to make it easy to manage the versioning and installation of our internal packages. High compute Python tasks, we're in the process of migrating to on-demand cloud instances. We can remotely start these, run tasks and shut them down. And so we can have virtual machines with more resources available, but we only pay when those things are on. And so it's kind of, an ideal state of high performance, but still low cost. So there's numerous data processing and computation tasks to make all this work. And we do, just like our encyclopedia, we have a sense of order. Prior tables need to first exist as a source for the current task. And so that is not exactly stateless, but once the table exists, they simply get updated. And so you could run these in any order. It wouldn't make a lot of sense. So we need some run logic to require that, or to handle that state maintenance. And then the automation for this is key. We want to automatically run these tasks in the correct order. This gives us capabilities for logging, understanding when the tasks fail or why they failed, automatically retrying those if there was just a network connectivity issue or some continuance, meaning the downstream tasks try to run and fail if the upstream did, or how do we know what downstream tasks should retry after the upstream task is successful? So we set up and use an Apache Airflow server to handle this. I like it because for our non-technical employees, you're able to see the dashboard, see what ran. You can manually trigger these tasks without having to remote in or SSH into AWS. So they manage the execution of stored procedures in our database. We can quickly diagnose any issue over several tens of thousands of lines of SQL code, and we can initiate a run of any task in this DAG, which is a directed acyclic graph, which is what this picture of all these, this flow chart you're seeing is called. And actually to do all this, we run it nightly updates from IHS public data. We process it all. This whole thing takes 15 minutes to run. It all runs on our SQL server. So again, SQL is very efficient. It's a lot of lines. It's a very declarative language, but it also makes it easy to debug when something goes wrong. And then we link this into external tasks. So we do probabilistic forecasting with Python. We're actually making use of some libraries to accelerate that. Numba, which uses LLVM, compiles to machine code for fast execution. And then actually using some of Derrick Turk's help, we've been able to parallelize that. And so it runs over all 12 CPUs available on my laptop. And we're able to get through both basins in about an hour. We do our associated phase, water and gas and SQL using that workflow I showed you where we had the hierarchy-based regression. And then we're able to use in some transformations of decline curve parameters based upon well spacing, parent-child status, et cetera, develop a machine learning process for transformation of those to normalize the production data, and then Krieg the parameters and develop type wells across the basin. And we do this at a section level resolution. So what does this get you? Well, on the front end, composability enables construction of dumb user interfaces. I say dumb because it's just displaying static data for the most part. And the idea here is to minimize the front end computation. Most of our calculations are regenerated daily and available through SQL queries. So we can turn these complex queries into parameterized queries where we can pass it a parameter and say, hey, just do it for this region or for this basin or maybe this flag to control some logic in that query. Or we just embed these as stored procedures where we just run them nightly. And so what we get out here is actual production data plus forecasts joined together straight from the query, and then minimal processing to develop a typo from that. And then some transformation of that on the front end where we compose factors for parent-child or operator tier performance or well spacing, which changes the red curve into the blue. And we can select that and we'll see the blue curve move up or down, which gives us a sense of performance or applying future development conditions onto type wells in this area or this piece of acreage. So summary and conclusions. I think integrated data systems are achievable for even the smallest companies. As an earlier question was asked, I am a reservoir engineer with, at one time, no formal education in programming, and I've just had a lot of practice by doing it for quite a few years to get to the point where I'm able to build all this stuff. Composability, I think, if we approach it as a design problem, which engineers love, it's a well-suited skill set for engineers. So the programming is just part of the design. But I think as Derrick said, you first consider what your design is. You don't just start coding. And then the point I want to make is low-cost hardware is capable of most of these tasks. We have a SQL server with considerable resources, not a huge one, but our data isn't big data. It's just public data, a few tens of gigabytes. What runs Airflow or REST API, whatever, is a small instance, one virtual CPU, 4 gigs of RAM, and it hosts, I think, 4 or 5 different web servers we're able to hit. And then for the Python stuff, I have a laptop, just a consumer laptop, not that expensive, even though it is somewhat of a high-end thing, but for commercial hardware, it's pretty cheap. With that, thank you very much, and I'm happy to answer questions.
And I'll summarize a question that came from the audience. How do you get your C-suite, your top executives, to buy into this kind of data cleanup process and the philosophy around better data? Because often they're blind to that, and workers just work harder in order to deliver their demands, deliver the C-suite demands. Any comment on that?
Yeah, that's a really challenging question. I think the big problem is this is traditionally seen as an IT role, and it's not visible. And so that's one of the challenges, I think. It needs to transition from being IT controlled to more of a cooperation between technical workers and IT. As we think about design, right, design needs to be iterated. It can't just be, preset and then fixed and static. And so there needs to be a sense of flexibility in working together. As far as convincing an executive, I think a lot of them buy into the idea of digital transformation and see, realize the potential value in terms of less time spent or dollars saved or better answers. I would say really the challenge lies in getting to see that none of that can be achieved unless you change the way your data culture at your company is set up, right? Rather than having it be people-centric, you have it be data-centric. And that means that requires people to develop different skills, develop skills working with data, to speak the language of data, which I think is, SQL, and how to query data, manipulate it, transform it, et cetera. So I don't really have an answer to that question. That's probably not a fulfilling response. I think it is a challenge. But I would say, the thing to focus on is the core fundamentals, not necessarily the end goal, how great it will be.
That's unfortunate. I was ready to take notes, but thank you. Thanks very much for the comments all the same. So let's move on to our fourth presenter. Thanks very much, David, for your talk and your comments. We'll come back to some more questions at the end of the discussion. Our fourth presenter is Tyler Schlosser, and Tyler is the Director for Business Intelligence at McDaniel & Associates, who are petroleum consultants here in Calgary. He has a background in reservoir engineering, economic analysis, reserves evaluation, and I think he's one of the most practical proponents of machine learning that I know in the industry. And so as such, I think he's a great person to speak to our next topic. So what? How do we communicate technical results to decision makers? Tyler, it's over to you.
Thanks a lot, Brian. Let me just share my screen here. So yeah, today I wanted to talk not about anything technical, I guess, but really just one of the common challenges that I see, certainly on the upstream side of our industry, where there's a lot of great technical work being done, and for the purpose of this, I'm just going to lump together the technical work and the sort of the analytics or the machine learning work. So you can kind of read one way or the other on that, depending on what's most relevant to you. But really, what I often see is that there's a lot of great work being done, but then for a variety of reasons, that work doesn't necessarily find its way into informing corporate decisions as well as it could. So, there's, I think, a variety of reasons behind this, but three of the most significant reasons, I think, are simple communication issues, human biases, and questionable or perverse incentives that exist at a lot of organizations. So what can we do about it? Well, let's look at a case study real quick. This is, I think, what is probably the most common application for so both sort of traditional subsurface work in unconventional plays, as well as the most common use of analytics and machine learning in upstream oil and gas today, certainly in terms of what's been done to date. And so we're going to look at a company who's looking to improve their well designs in an unconventional play. And their goals here are to identify the key production performance drivers for developing their lands and to essentially optimize what factors there are that are under their control to improve performance of future development in the field. So far, let's take a look at some of the relevant technical work that's been done to date by Generic Resources Limited, or GRL. So they have a simulation group who's done a study suggesting that frac spacing or cluster spacing is a very important aspect of the design that impacts performance. There's a note from their procurement manager that says that based on the 10 most recent wells, using local proppant sand rather than imported proppant sand provides about 10% cost savings. There's an analysis done by the reservoir engineers of all 100 GRL wells drilled to date, suggesting that drilling on strike, so drilling in sort of a northwest to southeast direction in this area, yields a 30% performance improvement relative to drilling just north, south, or east, west. And this comes at a 15% higher cost. There is currently no detailed geological model of the GRL land base, but there are plans to explore the impact of rock quality on well performance in the future. And some other engineers at GRL have put together a scatter plot of 500 nearby competitor wells from Awesome Energy, suggesting that if GRL just increases their proppant intensity by 50%, their wells should also get 50% more productive. And that's despite the fact that there have been a few recent attempts from GRL to use higher intensity that did not yield these anticipated benefits. So next, GRL completed an analytics study of about 1,000 reasonably analogous wells, including their own, as well as competitor wells, to investigate these claims and look to see if there's any other key performance drivers that weren't on their radar. And so let's see what this analytics study found. So the analytics found that tighter cluster spacing was indeed beneficial, similar to what the simulation study found, but only to about half the degree that it was found to improve performance in the simulation study. There was no performance difference at all among the different sand types that had any sort of statistical significance. And in fact, it was within the margin of error, but the local sand, which was cheaper, was actually found to be slightly better if you were splitting hairs. Once reservoir quality and completion intensity were accounted for, there was only a very small benefit observed to drilling wells in the on-strike direction rather than north-south or east-west. And using a map that was sort of automatically created from just batch processing all the vertical well logs in the area, there was a pretty strong indication that porosity and shale volume had a significant impact on well production performance. And finally, the one-to-one performance scaling from proppant intensity that was found on competitor lands only seemed to apply to the wells in the highest pressure areas of the play. And in GRL's case, their lands only have a very small portion which overlap with these higher pressure areas. And so the performance benefit on the lower pressure lands, which make up the majority of their land base, was only about 25% performance benefit for a 50% increase in proppant. So maybe not as good of a bang for your buck. So what were the stakeholder reactions to the findings of the analytics study? Let's take a look here. And for what it's worth, these are all based on actual experiences I've had. I kind of merged two different projects together to make it more interesting, but these are all legitimate things that I've come across. So the simulation group said, well, the lower sensitivity to cluster spacing found by the analytics study can be explained by our simulations too if we just tweak one of our assumptions. The completions manager said, the imported sand is way better and it's worth the extra cost. You can even see how good it is in a microscope. Look at this great well over there that used the imported sand. The exploit group said, well, that can't be right regarding the on-strike drilling. We're convinced that drilling on strike is huge. It's really important. And it easily makes up for the 15% increase in surface costs. And again, they pointed to their scatter plot showing that all the wells that were on strike were so much better than the wells that were not on strike. And the VP Exploration was just happy that somebody looked at rock properties and found them to be important. And he was keen to maybe do a little bit more work on that to build it into the company's understanding of their play. And at the executive level, there was limited engagement with the analytics study, but there was a sense of relief among the executives who really focused on the fact that despite their efforts to reproduce the superior performance of the nearby Awesome Energy competitor wells, the lower reservoir pressure on GRL lands was a factor that's outside of their control. And armed with the knowledge that there was this sort of thing that's out of their hands that was causing their performance to maybe be a little bit disappointing, they sort of took that to their messaging and to their investor presentation and suggested, well, maybe expectations should be lowered going forward, and that they felt that took a little bit of weight off their shoulders to reproduce the results that they were seeing on the nearby competitor lands. So the aftermath of all this, I guess, after the results were presented and after the immediate reactions, the simulation group built a new simulation study and essentially confirmed that, yeah, the lower sensitivity to cluster spacing found in the analytics study is plausible, and it's actually arguably more rooted in reality and hard data than our original simulation. And so they basically built a new simulation that now became what they called the most likely scenario that happened to agree with the analytics results. The completions manager was still pretty set in his ways, and I guess the rest of the executives just didn't want to deal with this issue. So to appease the hot-tempered completions manager, GRL continued to use expensive imported sand sourced through a long-standing vendor relationship, which was, quite a personal friendship between the completions manager and the vendor, despite the fact that they couldn't see any convincing evidence that the more expensive sand helped. And the completions manager thought the analytics stuff was hogwash. So in terms of the drilling direction, GRL wells continued to be drilled on strike based on a subsequent review of execution failure rates, suggesting that even if the performance benefits to drilling on strike weren't really there or weren't too significant, there did seem to be some execution risk benefits that in terms of the risk being reduced by drilling on strike. And so they continued to drill on strike despite the higher surface costs. The VP exploration, so basically the geology lead at the company, requested more resources from the rest of his team to improve the geological model based on the positive findings from the analytics study that suggested that the rock properties really mattered. However, the other executives thought that the performance could mostly just be determined by completion factors. They weren't convinced about the rock mattering a whole lot. And they were concerned that incorporating geological information would probably lead to their own land base looking less favorable, and they did not want that to essentially get out. So to this day, as far as I know, still at this company, after hundreds of millions of dollars spent on development wells, they do not have any meaningful internal geological model at all. And thankfully, there's only one company I know of who I can say that about. So finally, I guess the company pivoted their exploitation strategy to use higher completion intensities only in wells drilled on the highest pressure parts of the land base, and adopted a lower intensity strategy where there was less evidence that the increased intensity would make a difference. And finally, the executive team proudly announced their use of AI as evidence of GRL's industry leadership in the following month's investor presentation update. So when technical results or analytics results are presented to decision makers or executives, I guess I just wanted to go through some possible reactions, as well as some of the underlying thoughts that might be actually accompanying the words that are coming out of their mouths. And for what it's worth, I'm not necessarily this cynical about management and executives. There's a lot of really great teams out there, but I guess just to sort of highlight those difficulties that can occur and maybe how we might look to deal with them, I just thought I'd go through some possible reactions here. So one reaction that sometimes happens is, the executive says, "Ha, I knew it. Great job. That looks bang on to me." And really what they might be thinking here is that agrees with what I've already been saying, so I approve because, it makes me look smart or like I knew all along. Another reaction might be, well, we already know what we should be doing from that expensive study we did on our pilot well, so what you're showing me now can't be right. And what they really might be thinking is, well, if you are right, then we're going to look stupid for spending all that money before and completing our last 10 wells the way that we did. Another possible reaction is, from maybe some of the older school members of the team, that, this analytic stuff is a waste of time and we should just be doing everything by first principles. And one of the things that they might be thinking with that is that I think your statistical findings are wrong based on this one particular example I recall vividly. There's an incredible tendency for people everywhere to just remember those individual examples that really resonated with them. And a lot of the time, focusing too much on that obviously comes at the expense of what the broader trends are and the bigger findings are. But it can be great for marketing. Or they might be saying that because they just simply don't understand and have no interest in trying to understand it. Alternatively, it could be because the technical team did a poor job of clearly communicating the results and what they mean to the business. Another possible reaction is that, a model that doesn't incorporate, insert whatever factor you want to, but in this case, let's use microseismic as an example. If your model doesn't build this data in, then it just can't be trusted, because we know that that's a really important thing. And the underlying thought there, could be a few things. If there's a career risk element there, it might be that, well, my job is to analyze microseismic data, and so I really want it to be super important. And if it's not showing up as being really important, then that's a threat to me. Another reaction that might happen is, well, we already knew everything that you're telling us, so what are you saying that's new here? Why did we do all this work just to find out what we already knew? And again, the underlying thought there might just be, well, we did all this work, we as a management team approved this project and approved the budget for it, and there better be something surprising or novel here that was found in order for this to be perceived as worthwhile. Another possible reaction is, what would this look like if we measured it another way? So, maybe that doesn't agree with what the decision makers would like to be true, and it's very inconvenient. Or, in a more drastic sense, maybe if these results are accurate, maybe the company's actually in some trouble, and therefore, is there another way we could spin it? Or, again, can we use different data to maybe suggest a different conclusion that's more convenient for the company? Factors like that. And another reaction sometimes is complimentary of the technical work. So great work, we'll keep this in mind. But really, you get the sense that there's not really an intention to use the work, and it was more just of an academic exercise. And again, one of the underlying thoughts might be, well, I already know what I think. I have my mind made up already, so I don't really care what you say you found. I already have my view of reality that's not going to change no matter what. And again, another reaction might be, so what? That so what factor. What am I supposed to do with this? And again, maybe the technical team failed to portray, how does this technical finding link to a tangible decision that can be made that can affect the business? Or maybe they're just totally tuned out and they're thinking about what's for dinner tonight. Another possible reaction, this doesn't look right. What data did you use? Did you make sure to exclude those wells over there or those data points over there? And did you make sure to include those new data points that we got that look really great? Again, this is sort of usually fairly transparently an effort to say that, again, the conclusions don't support what we would like them to support, or what maybe messaging we've already committed to and said, we've told the world what we think already, and what you're telling me now will make us look stupid if we adopt that viewpoint. Or finally, we might get a genuine positive reaction where, and this happens a lot more often, I think, than we give decision makers credit for sometimes, is, this is excellent, interesting work, and we will adjust our plans based on what you've shown us. Or they might say, even more genuinely, the best insights are often the ones we don't want to hear, and we applaud your honesty and sometimes your courage for sort of telling us what we might not want to hear. And they might be thinking, well, we're lucky to have such great people working for us. So one reason I think that a lot of those earlier responses can happen in terms of the decision makers not being as receptive or as appreciative as they maybe might think they should be to some of those technical results is really a matter of incentive. So career risk is probably the biggest one, where people are just kind of looking out for themselves and what's going to make them look good, even when it sometimes happens at the expense of the merit behind some of the ideas. There's issues with performance metrics, either irrelevant metrics or poorly chosen metrics, or maybe the right metrics but the wrong thresholds in terms of goals for success. Route to success, sort of the yes man factor, or the sycophant, where being agreeable with your boss can look good for you. You can be associated with being a team player, but sometimes it causes a lot of people to kind of jump on the same bandwagon of maybe not the best idea, but it becomes almost taboo to speak out against it, just in the personal context of the company. Mental accounting is another big one, where we might see value in doing some diagnostics, that costs $500,000, and no one blinks an eye if that's on the completion AFE. But if a similar effort to understand things is put under the G&A budget, it might become a totally unacceptable cost, even though sort of the net benefit to the business is identical, and it's just an optics issue. Management compensation is, I would say, frequently misaligned with the company's best interests and shareholders overall. Yes, management usually owns shares and options and stuff like that, but a lot of the time, the thresholds that make sense for them are not the same as the thresholds or the goals that really make sense for the business as a whole. And finally, ignoring consequences. So we have these individual incentives that can sometimes dominate so much that the looking at sort of the aggregate effect of all those incentives sometimes can be, you're sort of missing the forest for the trees by focusing too much on specific individual incentives. And I'm not going to dwell on all these, but I guess another issue is cognitive biases. The technical team, I think, really has to watch out for things like clustering illusion, where they're so desperate or they're so eager to show a positive result that they maybe find patterns or find things that maybe don't really exist. And the availability bias, where the nature of our work is usually that we have access to some types of information or some types of data, and we might be missing other types of data that we believe might be important, but because we don't have the ability to analyze them, we sort of dismiss them as being less important, and we don't give them maybe as much attention as they deserve in explaining the uncertainty we have. On the management side, I guess we have, there's a lot of biases. I think the aggregate effect of these often makes change difficult. So if there are new results that maybe should be integrated into the business decisions, they maybe have a hard time permeating all the way through to action because of status quo bias or choice supportive bias, where we see that people tend to feel positive about a choice they made in the past, and they maybe look at it with rose-colored glasses, even if there's evidence that they should make a different choice next time. It might be harder to move away from what they did in the past. Another big factor here, I think, is just perception and reality. So a lot of the time, all of us are guilty of it, and certainly executives can be, of basically saying, well, we already knew that before. I could have told you this before, when really, we couldn't. Sometimes it's sort of like, yeah, I knew that, porosity matters regarding well performance, but again, being able to quantify how it matters is certainly something that maybe might not have been available before. And after this detailed technical work, maybe now it is possible to do that. And sometimes that, that factor is lost, and it can devalue the value added by very good technical work. I think ways that this can all be sort of helped, just to sum it up, I have just a couple slides remaining, I think. The technical team's understanding of the business problem and the context, as well as what the stakeholders actually care about. So what drives, the reason that the business exists in the first place, as well as being sympathetic to the pressures placed on decision makers. I think a lot of the time there's this sort of resentment that can occur between the technical team and the decision makers when the technical team feels undervalued. But I think understanding the pressures that the decision makers are under can sort of help grease the gears a little bit and allow the technical team to convey information in a way that will be received as more relevant and valuable to the decision makers. And the executive team, I think, should do as much as they can to engage the technical team on a regular basis, show interest in those intermediate findings while the project's ongoing, understand the rationale behind the process, and communicate the metrics of business importance to the technical team, so that at the end, when the project is sort of wrapped up, there's actually some company buy-in to use those technical outcomes to inform key decisions, rather than just a pat on the back and put the study on the shelf somewhere. I won't go through the obvious stuff. I guess just, the technical team should really know your audience, understand who you're talking to, speak clearly, don't try to look too smart, and explicitly tell people why they should care about what you're saying. And on the executive side, I would just say, be open-minded, be curious, try to leave the ego behind, and really do your best to help the technical team understand the business context in terms of what they're doing and how it can affect the business, so that really the business can benefit the most from that good technical work. And that's all I have for my slides. So thanks a lot, and happy to answer any questions.
Thanks, Tyler. That was very entertaining and also very insightful, I think. One question, when you've dealt with, you obviously talked to a lot of different companies, which engagements have been most successful? Like, what's been the have you had, what's been the common feature to an engagement being successful? Has it been the fact that you've had an executive sponsor all the way along, or has it been one where there's a certain culture amongst the executive team? Can you comment on that?
Yeah, I think it's obviously a combination of the things that you mentioned, but one of the big things I think is having someone at the company, whether it's an executive or just sort of a well-respected technical person who can sort of be, I guess, the champion for the project or for the effort, who can sort of say with some weight behind it that we're going to set out to do this, and we think it's really going to matter, and we think we should really look hard at what the results of this tell us, and maybe use that to change our path. And I think the companies that sort of have an organizational humility, maybe that's probably the single biggest way I would describe it, is just that ability to leave the egos behind, and if someone has a good argument that suggests with a lot of evidence behind it that maybe a different way of doing things could be better. Not having that that really hard baked in resistance where you say, no, we already are doing things this way, we're never going to change, or having one or two really strong personalities that sort of dominate the room, if you will, and make it hard for anyone else to sort of speak up or to work things out that might lead to a new path forward. So probably the one single biggest thing would be organizational humility, I think I would say.
The floor is open now for questions for all of our presenters. If you're interested in submitting one, please do. We only have a few minutes left in which to do that. I'll ask a question to the panel, which comes from Melanie. What do you think comes first if getting C-suite buy-in is important? Is it building the value of analytics via a demonstrated project, or is it asking for support in upskilling the organization? Would anybody like to take that one?
Yeah, so I mean, I'll go back to kind of what I said at the start, where I think the machine learning, the analytics, the AI is the destination, right? And we want to focus on why we're getting there, but I think the journey enables so much more. Once you get this, as I kind of try to illustrate, the tools and workflows orbiting the data and the composable systems, the idea is you can build whatever you want. So you don't just solve the problem of, here's the thing I want to look at today. You solve the problem of the thing you want to look at next month. And so it's really abstract, and it's unfamiliar to oil and gas especially, but you have to get them to see how having the pieces, the infrastructure, right? Just like we have to install facilities and pipeline to transport the oil and gas, drilling the well and producing oil is not the end product, right? I would say drilling the well is not even the end product. Owning the land is kind of the idea. That's the resource. And so we have to get to the point where we're getting them to see, owning the land is equivalent to being able to compose as we want, drill a well where we want, but the infrastructure has to be in place to make any of that happen.
Great, thank you. Derrick, I have a question for you that came from the audience. I think you're a good place to answer it.
Sure.
I think there's a kind of a lack of maybe software engineering and computer science discipline within some of the tools that are built in oil and gas. What would you say to somebody who had a background in one of those disciplines, who wants to get into the data science domain within oil and gas? What's a good way to do that?
Yeah, so it's kind of the inverse problem of what the typical engineer faces. But the solution looks similar, which is you're actually really well equipped to teach people in our industry things that they do not, by and large, know, and to really improve the way that some, especially the smaller companies, currently run their data science operations. So the key is a lot like for many of us who were petroleum engineers or worked as engineers in the oil and gas industry. It's pretty similar to what we did the first couple of years out of school. It's to show up, it's to ask questions, it's just to kind of relentlessly, in the same way I told engineers to pursue programming and data science, just sort of drill down to the atomic pieces and try and build up a vocabulary, right, a common language with the E&P industry.
Yeah, I think that's a really good comment. Like having the common language, the kind of shared understanding is a really valuable thing. That kind of a little bit of domain expertise that can go a long way. Tyler, which tools do you use? Which tools can't you do without? What do you use every day? Give us a hint of what we should be looking at next. That's the kind of power app. Oh, wait, sorry, no buzzwords. What's the
oh, buzzwords? That's going to be hard.
Your valuable tool.
I guess I don't know. I really liked Derrick and David's presentations just on building that foundation of how you think about and approach the problem, and and the topic that Melanie insinuated on really understanding what you're trying to do first is a really important thing. But in terms of tools, I guess I use Python myself as sort of my main tool kit environment to build everything in, and I just think that between Google, GitHub, Stack Overflow, pretty much if you just type in the thing that you think you want to solve, there's usually a great tool out there that already exists that's almost tailor-made for your problem. But to get a little more specific, I guess the two things I found really useful. One thing being, combining or at least trying a lot of different modeling types from the machine learning side. Try different algorithms, try different ways of pre-processing your data. Feature engineering is the biggest thing I think that requires the most domain expertise, but it's also by far the biggest difference maker in terms of the ability to understand and predict things from sort of that statistical or analytics standpoint. Especially in a way that's then going to be effectively communicatable to the executive team afterwards, right? Because those things have to be in a language that they understand. And so I actually think a lot of people maybe spend a little too much time on the data processing or data side and the algorithm, how much they think about the algorithms that they get used and stuff like that, when really I think probably the lion's share of the time could be deservedly spent on the feature engineering. And the only other comment I guess I'll make is that there are increasingly sort of good tools out there to help integrate or at least respect the physical relationships in statistical models and in analytics models. You can at least you can do things like enforce the directionality of a response to a particular variable. You can sort of build some structure in if you think that there's a physical equation that drives something. You can maybe start to build that in a little bit more. And so I'm, I guess, excited to see that sort of starting a little bit more to happen in our industry, and I think that's where we're going to see some really good results.
Yeah, I think there's a ton of value as well to be gained from that kind of interpretable machine learning component that you layer on top of the models as well. There's just the amount of depth that should be spent on interpreting and explaining results. The book that's out there, Interpretable Machine Learning, I refer back to all the time. With that in mind, like these kind of core resources or core tools, Shahab, I'll put a question to you. What's a really good resource that you think people should be looking at in the oil and gas industry that's kind of widely available? A book or a course or something like that?
Well, it's not an easy thing to do, in my opinion. And my understanding and my experience, actually, is I've been doing this for a very, very, very long time. And to be honest, in 1991, when I started this, I actually hired grad students with the background in electrical engineering and signal processing, because I thought that's what's really required to be able to apply this technology. They both graduated with their master's degree, but for us to get something and publish it, it took a very long time. What we did after that was hire petroleum engineers. So the question is, teaching petroleum engineering to a data science expert versus teaching data science or AI and machine learning to an engineering expert, which one is easier? Based on my experience, literally since 1991, is the other way around. As long as you get a domain expert that is strong, then for them to get the understanding of AI and machine learning, it's much faster, much realistic than the. I'm not saying the other way around, it is impossible. It definitely is not. It's just going to take a longer time. And a lot of time when you have a statistician, somebody with a PhD statistician, it's going to be very, very hard to tell them that you have to learn something else because they already know everything in the world. So so now what we looking at is developing a master's degree in petroleum data analytics, which literally from A to Z, the entire process is to go through reservoir engineering, reservoir characterization, drilling engineering, production engineering, every single one of them that they have done their BS in petroleum engineering, then they get the master's of how to solve the same problems using AI and machine learning. And the key is it's a different way of solving the problem, not using the same approach and then using AI just to make it look nice because I use AI. It's a completely different way. It's a philosophical understanding how you approach, how can data model the physics rather than equation and my today's understanding of what's happening.
And that's a good plug for what sounds like a comprehensive resource. When you said BS in petroleum engineering, I presume that's Bachelor of Science, but I'll leave that to the servers. John Thompson is going to say a few words now about Saga. But before he does that, I just personally want to thank our presenters and our introducer, Bimal Mehta. I want to thank Shahab, Derrick, David, and Tyler. Thanks very much. Really enjoyed your comments, presentations, discussion. John, it's over to you.
So thanks, Brian, and thanks panelists and everyone who registered for today's webinar and participated on the live stream. We really appreciate that. There's probably many of you in attendance that aren't very familiar with who Saga Wisdom is and what our startup is doing to be disruptive. So I just wanted to take a really quick moment to show our primary product, which is digital training in the petroleum sciences, which hopefully you can see on my screen share right here. This is our website. We launched in early 2019 with a course in rate transient analysis, which many of you probably associate with some of the founders of the Saga business. We sort of built our careers on it. And the RTA course is available with a couple clicks directly in our website. I encourage people to visit our website and to look at some of the free sample lessons that are available there. Recently, and more relevantly, we just launched Tyler Schlosser's course in machine learning for the upstream oil and gas industry. As you can see here, we've also got free sample lessons from his. I'm just playing a little bit of the intro. I apologize if it's a little bit choppy because that might just be because of my poor internet connection. But here you can see we've got online, on-demand, available options here for education in petroleum sciences with a real focus on subsurface from conventionals. So I just wanted to give you a quick sneak peek on what that looks like. Please check out our website and watch these lessons when you get a chance. I'll also draw your attention to the Saga Wisdom YouTube channel, where the recording from today's webinar will be put in place in about a couple of weeks. We've got a lot of things here. We've got other webinars from last May. We've got free technical lessons from Dave Anderson. We've got a series of flashy commercials from one of our founders, Darcy Fairbrother, who's in charge of the post-production editing of all of our media. And if you're looking to stay in touch with what we're doing, future webinars such as this one, other events and activities, you can just visit our website and go to the contact tab at the top, fill out your information, and you'll be subscribed to our newsletter. So thank you, everyone, for your support, for tuning in. We look forward to hearing from you.